Log on, tune in, find out. Another good idea from Cambridge.
Moss season, and in particular give this seminar. This is joint work with my PhD student, Kieran Meehan, and is really ongoing work. The further is supposed to indicate that we're extending some examples already known in literature, and these are due to Arcaro and Bertram, and I'll say a little bit about that, but not very much. We'll learn a little bit of that about those particular examples as we go along. So the main point of this talk is really to show you those examples. That's the core of the talk. I can't do that without setting up some background and some general information, so I'm going to do that first. I'm going to state some general results that enable us to deduce the wall structure and so on. And then I'll go through the examples. I'm going to go through 3 examples, although really it's an infinite family of examples. I'm going to do 3 in detail because the 3 simplest examples and each of the 3 exhibit different behavior. We think interesting behavior. So hopefully it'll be interesting by the end. And I'll make some concluding remarks. So that's my structure. So in the case of Arcaro and Bertram, they look at essentially Calabi-Yau surfaces. I'm going to look more specifically at an abelian surface, and I'm going to take a very specific one, essentially, which is principally polarized Picard rank 1, so irreducible, principally polarized abelian surface over C. I think I've forgotten to write over C on the slide there. So it's complex. So it's really rather specific. The advantage there is that we can generate a great deal of data, we get a great deal of information, so we can give a lot of fine structure to this. And in particular, and this is something I want to stress as we go through, I'm going to relate the moduli spaces of Bridgeland stable objects, I'll describe in a few minutes, to the geometry of this abelian surface, something I've been interested in for many years. So these spaces provide a kind of toy model, if you like, for constructing moduli spaces, in the sense that all the sort of behavior that tends to arise for moduli spaces of sheaves tends to arise for moduli spaces of sheaves on these surfaces. Okay, so in that sense, they provide good toy models for testing conjectures. So I'm going to look specifically at rank 1 sheaves. Oh, that's very annoying, isn't it? Oh, it's gone. I'm going to look at rank 1 sheaves, essentially corresponding to torsion-free twists of our polarization, squares of the polarization twisted by ideal sheaves of points, essentially. And I'm going to see what happens as we move away from, as it were, infinity in the stability manifold down to the kind of central core. In a sense, this is the simplest example with positive rank. And of course, in terms of Giesecke stability and mu stability, these are trivial. They're always mu stable and Giesecke stable. And as I said, we're very much following the footsteps of an excellent paper by Arcaro and Bertram, which I'm allowed to say is going to appear quite soon, hopefully. Where they look at the case of torsion sheaves, where the rank is 0 there, and there's an and C1 is kind of irreducible, and a very specific case. They look at a much broader class of surfaces, but they have perhaps a more restricted Chern character. I'm going to refer to it so often, I'll call it the AB paper, just to save me saying too much. Right, so here's a setup, just a rough summary of those who haven't seen principally polarized abelian surfaces before. Bit of notation, I'm going to have a line bundle L, which will be a line bundle corresponding to my principal polarization, curly L. There's a unique divisor in the linear system of L, which is a smooth genus 2 curve, and the torus can be recovered, of course, as pic naught of that curve. So that's all standard stuff. And notice that that divisor, the genus 2 curve, we can translate by pointing the torus. We're just acting on it via point x. And that lives in a translate of the linear system, which corresponds to a twist of the line bundle L. And that allows us to identify the torus and the dual torus. Now I'll do that secretly, and I'm never going to really bother with the dual torus except when I want to stress the fact that a point actually lives in the dual torus. And I want to just point out that there's an interesting geometry that rather parallels what happens with the projector plane. And in the sense that we can view these dx's, these genus 2 curves, these are all the genus 2 curves in our torus, they kind of play the role that lines would in the projective plane, in the sense that they have this kind of duality. That, of course, the intersection of any two is 2, right? L squared was 2, that's principal polarization. So the intersection, it gives us a point in Hilb 2 up to multiplicity. They intersect in generic 2 distinct points, but of course they may just touch. So we get a double point, fat point. But the converse happens too. Given any 2 points in the torus, they lie on precisely 2 of these lines. Okay. So there's a kind of duality there, and I think it's useful to think of these dx's as lines. So I'm going to call these lines from now on, and when things lie in them, I'm going to call them collinear. So for example, if a 0-dimensional scheme x lies in one of these dx's for some x, then I'm going to say it's collinear. Oh, color changed. That's nice. Okay, so that's the kind of geometric setup. So, what am I really going to talk about? I'm talking about moduli spaces of objects. Okay, and this, I'm going to look at the Bridgeland stabilities, which were essentially the ones introduced in the AB paper, and indeed by Bridgeland in his original paper on Bridgeland stabilities. And in fact, really these stability conditions were thought up originally to try and explain something to do with the torus, and I'll try and mention that as I go along. So actually the foundations of Bridgeland stability conditions really goes all the way back to trying to understand things to do with moduli spaces of sheaves, and I'll mention that as I go along. Right, so we have, I'm not going to get bogged down in too much of the theory of Bridgeland stability, because we don't really need that much of it. In particular, I don't really need the stability manifold, because I'm going to look at specific points. And if you remember, the way it works is we have a stability condition, essentially, or a particular choice of one, we can take as an abelian subcategory, which I'm going to call A beta. Beta is going to be a rational multiple of the polarization. Okay, and the A beta is an abelian subcategory that arises at a tilt of the category of coherent sheaves, thought of as atomic objects, in position 0 in the derived category. In the usual way, we have a kind of free part, the F, okay, where we take the torsion-free sheaves whose maximal slope of Harder-Narasimhan filtration is bounded above, but essentially by, as it were, the kind of beta, a kind of slope number, if you like, and a torsion part, T beta, which consists of the torsion sheaves, or where the free part has its Harder-Narasimhan, its mu Harder-Narasimhan filtrations bounded below by beta. So beta is a rational multiple. Actually, if you want a continuous manifold, of course, you need a real multiple, but for us, actually, rational is all we want to think about. And then there's a z function, kind of charge, if you like, okay, which is, as usual, linear map from the K theory. And for these particular ones, we're going to choose a specific charge, namely the one where we pair e to the beta plus ITL against the Chern character. So it's certainly linear in the Chern character. Okay, that then I'm going to throw that away now. Pretend it's not there really, and replace it just with the slope, because we only ever need the slope function. So there's a slope function from this, which is essentially the usual slope function. It's really imaginary over real, but we turn it the other way up to make things work. And in this case, it computes to that formula, as it happens. Okay, and that's not going to concern us too much because we're going to set beta equal to 0, so we can ignore beta really in essentially what follows. Okay, so this is very much the setup in the AB paper as well. Okay, that then allows us to define stability in the usual kind of way. Every non-trivial subobject in A beta, remember AB is a abelian subcategory, so this injection from beta is in A beta, not in co. Has the slope of B must be less than the slope of A, okay, for any proper subobject. And the aim is to find, to try and look at fine moduli spaces, okay. Of course, in some cases they'll be empty. We know now that there are a kind of stacky construction that tell us that there always is a stack. But the moduli spaces, if we actually want something representing the stack, then they may be empty. They may, of course, generically, they're going to be coarse. They're not going to be fine moduli spaces. So we're only going to look at ones that are fine. And the name of the game is these fine ones should be projective varieties. That's what we hope will happen. So that's the kind of standard moduli functor. The standard bit of theory, again going back to Bridgeland, is that if you pick one of these a betas, and remember we have a t parameter as part of our slope function up here, so we think of t going from small t up to infinity, and as when t is very large, these moduli functors are co-represented by moduli of essentially twisted Giesecke stable sheaves. Okay, so in the big limit, we have a kind of GIT construction for these moduli spaces. Okay, that's standard theory. And now just make a few observations. So if E is torsion-free whose mu plus is less than beta, and it happens not to be actually locally free, if it's properly torsion-free, then notice that E is not actually in A because the way the tilt works is that F goes in position -1. So if I shift it by 1, this is now in A beta, but it's never T stable. Okay, and that's a kind of standard construction where we take E to its double dual, okay, and the double dual is also in F beta, but the quotient, the sheaf quotient, is a structure sheaf of a knot scheme, and of course it's in T beta, so I have to shift it by 1, put it on the other side, and it destabilizes E, okay, always, because it has infinite slope. So we have these kind of, this is supposed to be a little warm-up exercise for the audience to get us in tune with how it works. So the case, I was loath putting this down to kind of make a connection with the numbers in this paper. In terms of our beta, this is the Chern character that they deal with in the AB paper. Actually, it can't be quite this because they need one that's actually irreducible. So beta needs to be a half integer and not an integer for this to actually apply. But I'm going to try and draw some parallels with it using these Chern characters, as you'll see as we go along. Right. So that's stability. The other tool I have at my disposal, by focusing specifically on the principally polarized abelian surface in particular, is a very nicely controlled family of Fourier-Mackay transforms. Okay, and remember how they go. So this gives us we have a Fourier-Mackay transform for me, unlike Huybrechts. These are invertible. They're invertible equivalences of categories ds to ds dash. Okay. Which are given by an object on the product, the derived category of the product. You pull back, you twist, and you take the direct image. And I've liberally sprinkled it with L's, a lot of the time that's not necessary, of course. And I'm going to set the convention, which again is Huybrecht's convention, of shifting by 1. Okay, and that means that typically, if E is a vector bundle or a sheaf, say, and A was a sheaf, then on a surface we would expect these to have cohomologies in position -1, 0, and 1. So I'm shifting it back by 1.
Is that anything to do with the fact you're on surfaces? I mean, in different dimensions, would you shift by a different amount?
No, it's to do with the fact that I want to tilt, and the tilt is -1, 0. It's actually just a convention. If I made the tilt 0, 1, I wouldn't shift at all. But whether it preserves one of my abelian categories will depend on the fact I'm on a surface. So that's going to be critical too. And this is the advantage of focusing down on a principally polarized abelian surface, is that the set of these Fourier-Mackay transforms, that's actually, of course, it's a group, but as a set, it's actually quite small. It's actually indexed essentially by a rational number. So given any rational number, there is a vector bundle whose universal sheaf gives rise to a Fourier-Mackay transform. Okay, and of course we can shift them to get another one, and we can twist by line bundles pulled back from the second factor, which is the equivalence of E. Okay, but up to that, and we can think of that as a slope of this vector bundle. Okay, and the point infinity corresponds to the identity Fourier-Mackay transform, whose kernel is O delta. So this is O delta, the structure sheaf of the diagonal in T cross T. So given a rational number Q, I'm going to let the Fourier-Mackay transform just be phi Q. Actually, I'm going to set Q equal to 0 very soon anyway. And a rather beautiful observation of Huybrechts in a paper, was it 4 years old now, 3 years old, was that in this kind of context for K3 and abelian surfaces, that given a Fourier-Mackay transform, we can always find a pair of parameters beta and beta dash and t dash such that the Fourier-Mackay transform restricted to the abelian subcategory maps to a corresponding abelian subcategory in the derived category of the image space. Okay, and moreover, the slopes are preserved. Okay, in particular, this means that the Fourier-Mackay transform always preserves stability in this sense. Okay, so that's the key. So in particular, it's going to automatically send moduli spaces isomorphically to moduli spaces. Okay, and that gives us, it kind of doubles the number of hits we get, as it were. Okay, and we use that extensively in what follows. So as I said, phi q always preserves stability. The classic example is Mackay's original Fourier-Mackay transform is the case q equals 0 given by the Poincare bundle, and actually that's the one I'm going to use today. Okay, and in that case, it's easy to see that beta is actually 0, beta dash is 0, and t dash is 1 over t. So this is rather nice because this actually fixes a naught. It sends a naught to itself. And remember, the torus and the dual torus are essentially the same space, particularly given I fixed the line bundle L, they actually are the same space. Right, they're canonically isomorphic, so I can essentially identify them. So I'm going to do that in this talk. So what this means is it's going to send the moduli spaces for big T to moduli spaces for small t. Now the big T ones we know, they're essentially given by geometric invariant theory, and they're projective, for example. And automatically I can just read off that their Fourier transforms are therefore projective varieties, isomorphic to the GIT ones. So we'll use that for one of our examples, as you'll see later. Okay, and now I'm going to set beta, oops, I'm sorry, hey, hello. I'm going to set beta equal to 0. Okay, because I'm going to want to use this particular transform. So that's my setup. So let me just recall some general facts, kind of standard things. So the name of the game is to try and describe what are the objects in the possible moduli spaces. Okay, so the first thing we can ask is so in other words, which objects in A0 are t stable for some t? Okay, notice that an object is, if it's stable, then it's simple. Okay, that's Schur's lemma. That's a standard fact. The only automorphisms, well, in this case, we're working over C. The only automorphisms are multiples of the identity. If I have a sheaf which has, now the beta is 0, so if I have a sheaf whose mu plus is less than or equal to 0, okay, then if I shift it by 1, it's in A0. Okay, and in that case, it has to be mu semi-stable. There's no room to destabilize it. Okay, and the same happens in T, as it were. So if I've got a sheaf in T, so this is now in A0, it's already in position 0. If it's got minimal degree, as it were, okay, then E over its torsion is mu semi-stable, or it may be 0, of course, if it's a torsion sheaf. And in particular, if it's actually a pure sheaf, so either it's a torsion sheaf pure on its support, or it's a torsion-free sheaf properly, and then it has to actually be t-stable for all t. So this automatically constructs a whole set of moduli spaces for us. Twists of L by themselves are, positive twists are certainly in A0 because they have positive degree and they're always stable. Negative twists, of course, are not in T anymore, they're in F, so I have to shift them by 1, but they're also t-stable. It's easy to see. As an application of 3, if I take the ideal sheaf of some points and twist by L, okay, that's got degree L, C1 is L, and so I can apply 3, and that tells us that it's t-stable for all t positive as well. And it's a good little exercise to check, in the case that I'm going to be interested in, is L squared tensored by the ideal sheaf of points. And that's stable whenever I take either 1 point or 2 points. Or no points, but that's covered in 4, of course. Okay, and again, they're t-stable for all t, so there are no walls, in other words. So there's some kind of general warm-up exercises. So here's the thing that makes it all work. This is the proposition that tells us what are the possible things that may be t-stable for some t. Okay, so the Chern character we have, as I said right at the beginning, is we have rank 1, C1 is twice L, and the Euler characteristic, so normally I would use Mackay vectors here, but the Mackay vector and the Chern character are the same for a torus, for abelian surface. So the top part of the Chern character is the Euler characteristic, and so I'm going to set that to 4 minus n okay, because then n is the length of my ideal sheaf for a torsion-free point. Okay, so either, then we already know that when T is very large, the standard Giesecke moduli space, which consists of torsion-free sheaves, rank 1, okay, which therefore have to be of the form L squared tensor. I'm going to drop tensor product signs, you'll realize soon after a while. Tensor, the ideal sheaf of n points, including fat points, of course, twisted by flat line bundles, precisely parameterizes all of those points in the moduli space for large T, right? Because they're the Giesecke stable line bundles. Of course, that's a rather boring case. However, some new cases do pop up in this case when n is 3 and above. And one thing that can occur is that you can have a sheaf with torsion. In that case, the torsion can only be supported on one of our lines, okay, and of a specific degree. Okay, once you restrict it to the genus 2 curve, its degree has to be 4 minus n plus m. Okay, it's a sheaf with torsion. If you mod out the torsion, then it has to be torsion-free, of course, and rank 1, and it's given by m points on the torus. Okay, so this very much narrows down the possible T-stable objects. Okay. Moreover, there's a fairly tight bound on m, and in fact, from this we deduce, in fact, that when n is 2 or less, actually there can't be any. This case doesn't arise. Just reinforcing what I said on the previous slide. But rather curiously, this is a really weird thing, which surprised me a lot when we found it, is that there's an exception to this, but which only happens when n is 5, for 5 points on a torus. It doesn't happen for 3 or 4 or for the rest of them, but only for 5, rather curiously. And that is, we end up with what is really a rank 2 destabilizing object. In other words, the following complex, whose minus first cohomology is the L inverse, essentially, and whose 0th cohomology is now a rank 2 vector bundle, which its Chern character is forced to be C1 as L, and all the characteristic is 0, that forces it to be a mu stable. Well, we know it's mu semi-stable. It's forced then to be mu stable and locally free. And that's it. That's all that can arise. Okay. The next thing you have to observe is that they really do arise. Okay. So we need to actually construct them. Doing the last case first. If you pick a point in A0, so it's a 2-step complex whose cohomology is minus first cohomology is L inverse, and 0th cohomology is this rank 2 vector bundle with that specific Chern character, and then it turns out whatever it is, then its Fourier-Mukai transform has to be a sheaf. Okay, and not only that, it has to be a torsion-free sheaf. Okay. Now, the particular Chern, and remember, this case only can arise when n is 5. And when n is 5, let me just get a little bit of chalk. When n is 5, the Chern character we're interested in is 1, 2l minus 1. And when you apply the Fourier transform to this, you get the same thing. So this is precisely the case where this Fourier-Mukai transform that sends A0 to A0 actually, well, it doesn't quite fix the space, but it sends the space to itself. In fact, it kind of moves it about. Okay, and of course the other cases don't do that. Okay, so the transform is actually one of these things. And so in particular, this case does arise because I just apply the inverse transform to one of these and I get this case. Case 2, on the other hand, we can show that such an A that I've written down has to be T-stable for T in some bound. Okay. So this is actually the wall that you cross, okay, and so you have a torsion-free sheaf which is stable for big T, and as T decreases, you hit a wall at this T when T is this value, and you have to put in these torsion sheaves in their place, and they remain T-stable all the way down to here, guaranteed. Okay, so that guarantees that these exist. However, it's not guaranteed that they'll remain stable beyond that point. And in fact, unfortunately, what happens is some do and some don't. And this is quite different to what happens in the AB paper, where these sheaves remain once you've put in well, in that case, they have two-step complexes. They remain stable all the way down to their kind of nasty higher rank wall. So that's a rather different phenomenon, rather complicates matters. Then we can link it in the general case to the geometry of the torus. And that allows me to say exactly what the bound is beyond which all the moduli space is given by torsion-free sheaves. Okay, so it's kind of, if you like, the Giesecke space. At some point, these moduli spaces turn into the Giesecke space. The question is, what is that bound? And here it is. This is the hard bound, and it's phrased in terms of the geometry. Okay, and here it goes. So what is it? What is it? It's that the wall occurs precisely when there is a collinear subscheme of X, okay, of maximal length. Then E is constrained to be T stable for all T bigger than this, okay? So the wall occurs when X double dash equals X, okay? And the length of that's N, okay? So that tells you precisely where the wall is, right? Root N minus 2. So that's the top wall. As I said, that bound is tight. So that's kind of the general data we have, and from that we can just kind of construct examples. And the examples it's worth doing that because the examples exhibit all sorts of curious behavior. Okay. So I'm just kind of collecting all that information together. What do we know? Well, if we have this one parameter family of stability conditions, I'm going to fix my abelian subcategory as this A0. And then I have mu t varying, kind of slope function varying. Then the moduli functor kind of hits, as it were, n minus 1 over 2 walls. Okay, for n positive. Notice when n is 1 and 2, that equates to 0. So there aren't any walls. Except when n is 5, when I get an extra wall. Right? That's a really curious thing. So the number of walls are 0, 0, 1, 1, 3, 2, 3, 3, 4, 4, 5, 5, and so on. It's really curious. And rather unexpected, I have to say. Just to try and picture it, if we number the walls 0 up to this number, minus 1 because I'm starting at 0, backwards as it were from the top wall, then we have n plus 1 over 2 fine moduli spaces. And I can say they're fine moduli spaces from the AB paper because they're computation of the Mukai flops going from one moduli space to the next one, going through the surgery, translates immediately to this context as well. So automatically we have these fine moduli spaces. M0, of course, is the original Hilbert scheme, essentially.
You do mean a series of Mukai flops when you cross only one wall, is that right?
Yeah, so the first wall you get a Mukai flop, yeah. A single flop, except as we'll see when n is 3, as it happens.
But when you cross
generally.
walls.
But subsequent walls you have to do multiple flops because I've got these substrata inside that I have to surger out and then surger back in again. Right.
There's many walls.
Uh-huh.
Walls composed of many walls.
Exactly. So what you get is a kind of a conjugate Mukai flop, I would call it, because you have to undo the Mukai flop, do another one, and then redo it. Uh-huh. So it's a kind of conjugate Mukai flop. We have the added complication that only some of these things become stable. So we have, actually I'll show it. We'll see it in the example actually, because the length 5 case has an example. So as I said, these are related by essentially a series of Mukai flops. Okay, at each wall. So what I'll do is, rather than saying anything more general, let's go through the examples. So I'm going to start at length 3. I'm going to do length 3, 4, and 5. Okay, they're all three of them exhibit rather different behavior. 5 we've seen is a bit weird because it's got this higher rank destabilizer. So in this case, there's precisely one wall, as it happens at t equals 1. There's our Giesecke moduli space, which is, so I'm going to denote the Giesecke moduli space is just by m and then raised to the Chern character. And then so there's another moduli space after we cross the wall, which I'll call m1. In this case, the bad locus is I'll explain in a minute, is a P1 bundle over a product of tori, but it exists in codimension 1, so it's not going to be a Mukai flop. And in this case, the exceptional locus is given because they correspond to y being collinear. Okay, in that case, we have destabilizing objects just given by twist of L. And the quotients are then line bundles supported on some translator D. and it happens that the degree is 1. Okay, so these are torsion-free objects in M0, and as you hit the wall, these things are destabilized by these L's, and so we have to glue in the reverse. So we do a surgery by replacing these sheaves with the equivalent sheave with torsion. So I take an extension with the T and the L swapped. Since the dimension of the X group you can easily calculate as 2, the exceptional locus is, we can think of itself as a moduli space, a kind of Brillnosa locus in a sense, which we can view as a P1 bundle over the parameters, and the parameters here are just the x's, x hat, x, and the flat twist that goes into T. So it's a P1 bundle over T cross T hat, to be precise. So in NM1 we put in we glue in the dual bundle. So we're doing a kind of Mukai kind of construction, but it's not really because it's codimension 1. Sorry, yeah, maybe I'm going to...
That would be my next question. Yes, are they isomorphic?
In fact, they're isomorphic, and in particular, M1 is projective. Okay. However, they're not isomorphism because this restricts to an isomorphism. The birational map between M0 and M1 does not restrict an isomorphism. They're isomorphic for a different reason, which I'm about to explain. And in fact, I don't think that is an isomorphism.
You mean
The natural birational
map does not extend to a biregular.
No.
But how? I mean, if they could have mentioned 1, what is it?
It's just a nasty surgery. And in fact, in fact, I think they can't be isomorphic. However, I'm going to prove they are isomorphic, and we'll see that isomorphism definitely doesn't restrict to the identity on the locus that's preserved. And here's how it goes. It's quite interesting. The trick is, and here's the extra data we have. We have the Fourier-Mukai transform. Now, if you apply the Fourier-Mukai transform to this particular Chern character, in this case we've got a +1 here. Okay, what phi does is it just flips the Chern character over and changes the sign. So what we get is -1, 2L -1. Now that, of course, isn't the Chern character of a sheaf anymore. Okay, the generic element in this moduli space is going to be a Fourier transform of a generic one of our ideal sheaves, and what you get is a two-step complex. So E is a generic element, and I can express it like this as an extension in A0. Okay, so this is its H1, H -1, and this is its H0. However, as luck would have it, the converse more or less works. If I take such an element that has this cohomology and apply the Fourier transform to it, so it sends triangles to triangles, it's exact. So the transform of this is just a rank 4 vector bundle. Okay, here. This is the transform of E, and as Mukai showed way back when he invented Mukai transforms, the transform of the structure sheaf of any number of points is a homogeneous vector bundle. Let's say a flat vector bundle of the same rank as the length of the knot sheaf. And because my transforms are all shifted by 1, I have to shift by 1 here. Okay. So, bear in mind, this is an A0. So, however, this is a sheaf, and if I want this to be a sheaf, I have to move this to the other side, and I have to ask that map inject. Okay. So phi of E is a sheaf in M1 precisely when that map injects in co. Or in other words, if we go back to here, the map from here to here kind of surjects in A0. That's another way to think of the same thing. Moreover, the automorphisms of this guy are very large. So the quotients of this are gobbled up by its automorphisms. So in particular, the moduli, the quat scheme here, is precisely given simply by the parameters y, well, y twiddle I've got here, and y little y hat. So in other words, a point in the dual torus and 3 points on the torus. In other words, well, actually let me work backwards. In other words, this moduli space I've just constructed is precisely Hilb 3 cross T hat, which happens to be M0. But the map here, well, the map there is just identifying M0 with this Hilb scheme. The map here that identifies this one with this one and then with this one, it turns out to be, if you restrict it to the generic point, is not the identity. And in fact, it turns out to be the following matrix. No, whoops, that's not going to work at all. It turns out to be that. We can think of it as acting linearly, as it were, on the torus, because you can add. Okay. So it's definitely not the identity on the generic points. And in fact, you can see that already when you construct Fourier-Mackay transforms, because this y twiddle, which is the Fourier transform of these guys, although this y twiddle is isomorphic to y as a scheme, is not equal to it. You definitely get different points. So what it's doing is it's taking this moduli space with its P1 bundle inside it, and it's kind of messing around the outside and then gluing in the P1 dual. So in other words, you glue the P1 back in, but you mess up the outside. You don't get the identity map here. However, M0 and M1 are still isomorphic. Okay, I was rather hoping they wouldn't be. Okay, but it turns out they are. There's another way of seeing it, which links nicely with the AB paper, which is that isomorphism can be given directly by just taking the dual. Okay, if you take the derived dual of L squared I y, where y are 3 points on the torus, then you get one of these two-step complexes, and it turns out that it precisely preserves moduli. That's always slightly delicate because the derived dual doesn't preserve A0. It doesn't send A0 to A0, unfortunately, so it doesn't preserve stability on A0. So you've got to be it's a little delicate. It's better to go the way I did it. But you can prove it directly with this too, if you want to. And while we're on the subject, since I have this Chern character, we can ask, well, what about the moduli space of these guys? When T is large, there are precisely those two-step complexes we had on the previous slide. Okay, what happens? Well, it too has a wall because their moduli spaces are isomorphic to the moduli spaces of M0 and M1. What happens when you cross the wall there? And the answer is that you have to do a surgery, again, in codimension 1, and you have to glue in different two-step complexes on a stratum. And it turns out that their cohomologies are L inverse and a torsion sheaf supported on one of these lines. Okay, and of course they precisely correspond to the Fourier-Mackay transforms of the collinear IYs. So that links back to the geometry of the torus. And of course, again, although it's a different moduli space, it's still isomorphic to the original one. So all our moduli, all 4 of them are isomorphic. And in fact, these points actually correspond essentially to the dual, and I'm trying to use the notation in the AB paper, that the dual of the ideal sheaf, twisted ideal sheaf. Okay, but in there, they were T-stable for all T. So in this case, we hit a wall and they're not T-stable anymore, which is quite interesting. So. But I stress again that the Chern characters don't quite work out because our one's reducible and yours isn't. So that's why. Right, that was length 3. Length 4 is actually rather more boring, if you're not already bored. This is even more boring. There's a single wall still, this time at root 2. And what happens here, you notice I've got different letters for these knot schemes. This is a conventional one, which I rather like, I'm very pleased with, and you'll all groan when I tell you. So I use P for 1 point, Q for 2 points, Y for 3 points, Z for 4 points, so Q tangles you see are a point, and W, as we'll see, for 5 points. The English language is not capable of doing 6 points, so that's why I'm only going to do the first 3. Right. So I need Cyrillic, I think. Yeah, exactly. I need a different alphabet. The English alphabet's not capable of doing it. Yes, so. Sorry, that was a little aside just to wake us up because we're feeling a bit bored. Right. So Z, so I use Z. So Z, as soon as I see Z, I think, length 4 subscheme. So I've got length 4 knot scheme. These are interesting because these are used to construct vector bundles whose Chern character are 2, 0, minus 2. And you might think that's a bit boring. What's that all to do with? Because these are the Grady spaces that produce a new, well, they're not new now, but they were at the time, new symplectic compact hyperkähler manifolds. So these are kind of crucial there, although we don't gain very much information about them from this construction. So again, there are 2 spaces, 2 moduli spaces, an M0, which is the Hilbert scheme, and M1. Okay. And in this case, M0 and M1 are not isomorphic, although, I mean, not that we've proved that they're not isomorphic, but they're Mackay flops of each other in codimension 2, and they're not obviously the same. That's about as far as we can go. They might be isomorphic, but I think it's very unlikely. However, M1 is still projective. Okay, so that's a little step forward. And the proof is one line. It's simply the observation that if we hit the points of M1 with the Fourier-Mackay transform, then the Chern character in that case gets sent to 0, 2L minus 1. That's of course torsion sheaf. And then the kind of Carlos construction kicks in and we get a GIT construction and they're projective. As I said, I wouldn't expect M0 and M1 to be isomorphic, but we don't know that they're not. Just a few comments about that. While we're on the chart, have the 0, 2L, -1. These are torsion sheaves, so this links with the AB paper rather closely, and I just want to draw a parallel there. Remember, T is sent to 1 over T, so my wall at root 2 is sent to a wall at 1 over root 2 now. Okay, those points, of course, are all T stable when T is bigger than 1 over root 2. When we cross that wall, you have to glue in two-step complexes, just as happens in the AB paper. What you glue in is not the dual of an ideal sheaf now, but actually the ideal sheaf of a point, and as it happens, L inverse. To make it closer to the AB paper, we can shift our A0 to the case they consider, which is AH squared over 2, which in our language is A2. And in that case, the Chern character twists up to 0, 2L3. Again, it's not quite their example because they need beta squared, so it's really 4 in their paper. And in that case, there would be a wall at a half, if only it weren't reducible. And probably a wall at a sixth as well. Okay, you got a single wall there. And there, you have to glue in things that have whose cohomologies are L to the -1, and that's not a typo, it's just that you have to untwist by L. And also the dual of IPH, which is exactly the situation there. So it's very similar, in fact, very analogous. So that's the length 4 case. Length 5 case, I got bored writing out lots of symbols, so I thought I'd just draw pictures. So I've got 2 pictures to show you, basically. Now, remember, this was this anomalous case. This was a case where we had an additional wall over and above what we should have. So we have 2 kind of normal walls here and here, and we have this kind of higher rank wall down here, corresponding to this rank 2 vector bundle at Chern character 2L0. So there are 4 moduli spaces to contend with, an M0, which is our Hilbert scheme. Then we cross the first wall and we do a flop, okay, via some M-twiddle down to M1. The surgery we're doing here is in codimension 3 now. This is a P3 bundle over some space. So we do a codimension 3 surgery there, a Mackay flop. Then we hit this wall. This is codimension 2, and we do a codimension 2 Mackay flop. And then at this wall, this is also codimension 3 again, and we do a flop again. But as I said before, for this particular Chern character, the Fourier transform actually fixes the Chern character, so it acts on these spaces. It just switches them about, and since it sends T to 1 over T, what it does is it sends M0 isomorphically to M3, so these spaces are isomorphic, and it sends M1 to M2. Those spaces are isomorphic by the Fourier transform. Okay. So that's the picture. And
that means
yes, do.
Because of this symmetry, there would have to be another wall.
Yes, absolutely. Yes, I mean that's right. Though that's what forces this to happen. The wall is forced on us by the fact that the Fourier mechanic acts on these spaces. That set of moduli. Okay. I mean, there's another reason. There's a sheaf reason as well, of course, which is what we came to first. But yeah, it's going to have to be. I mean, we knew a priori somehow.
Well, why is it only forced that in case of length 5?
Well, because the other ones, it's only that one that fixes it. As soon as if you put 4 minus n, you see that gets swapped to here. So it only works when n is 5. That was easy now. So it's a strange thing. Let me just delve down to it a little deeper. I'll need to explain this picture. Let me highlight some of it. So what I've done is that I've kind of glued them all together. You can't really glue them because, sorry, let me just flip back 1 second. I mean, these inner spaces are isomorphic. These spaces are isomorphic, so there's 2 isomorphism types. It's very unlikely that these guys will be isomorphic. I mean, they may be, but it's very unlikely, okay? So I don't want to give the impression here that these are isomorphic, but I've kind of put them on the same picture just to kind of try and show you how it all ties together. So you're supposed to think of these moduli spaces vertically. Imagine taking a slice through these 4 slices to give the moduli spaces. And what I'm showing as you go up are different flavors of sheaves or objects, okay, of different types. And I've drawn the walls at the top. A wall at root 3, that's the highest wall, a wall at 1, and a wall at 1 over root 3. And the vertical walls represent a wall that you have to do a surgery on that sheaf. You have to throw that sheaf away on one side or object and put in a new object on the other side, okay? So that's what it exhibits. So what do we have? Well, the top wall occurs when we have a destabilizer of L. That means that our W, remember that's 5 points, because we have 5 points, is destabilized by L, and therefore W itself must be collinear. Right? That's precisely what it means to have a map from L. Okay, any map from L, of course, must inject. It must therefore, that implies that W is collinear. So that's a kind of geometrical bit of information. So when it's collinear, that's the ones that get surged at the first wall. Okay, the rest, however, remain stable through that wall, so they persist, so there's no wall there. As we go down to the next wall, there's another wall occurs here where we have a map from LIP, where P is a single point. And that means that there's a collinear length 4 subscheme in W. Z, remember, has 4 points, so it's length 4. So we have a collinear length Z corresponding to a map from LIP. Okay, and that's what happens from that point down to there. We surge those out. However, and this is where things differ from the AB paper, some of these ones that I've glued in, these are now sheaves with torsion, also become unstable, and we have to surge them at the same time with the same surgery. Okay, so the actual combination of surgeries is rather more complicated at that point. And then as we continue, the wall at 1 over, this is our new wall that really shouldn't exist, at 1 over root 3, the higher rank wall, occurs because we have, and here's a geometrical situation, there's a unique, and I've forgotten the word unique here, a unique collinear Y in each Z in W. That's a very curious condition. Okay, so I take 4 points, okay, I've got 5 choices of 4 points in W, generically at least. Okay, and each one of those 4 must contain a collinear 3 points. Right, remember, any 2 points always contains in a line, 3 points may not. That's a collinear 1 condition. Okay, but every Z has to contain that. So that's the geometrical condition that makes me hit a wall. But it turns out rather horribly that some of the ones I've just surged also hit the wall as well. That corresponds to the fact that, can I just move that for just 1 second? If you remember, we had this diagram. Oops, that's the wrong diagram. We have a rank 4 thing. So what shall I call the rank 4 thing? E. No, the rank 2 thing. So this is 2L0. This is my funny vector bundle. Okay, and then I have something like L inverse, and I take a quotient. Okay, and these quotients, of course, are not always guaranteed to be torsion-free. Sometimes they'll be torsion, and the ones that are torsion are the ones that live in here. So that precisely describes those points. Okay, so then I have to combine those with these torsion-free ones that satisfy this geometric condition, and then I have to surge all those out. Okay, and then I now glue in 2-step complexes here. And of course the generic W's remain stable the whole way down. So here's the picture, and you notice it divides up into these beautiful symmetric regions, and these regions are related by the Fourier transform. So if you read the diagram from the right inwards, everything remains a sheaf, right, until you hit a wall. So we have this kind of step pattern, and all of these guys are sheaves. So the Fourier transform of these guys gets sent to here. Okay, so a generic L squared IW is sent to L squared IW, but it's not W. Just as we had with the length 3 case, where the Y was sent to a different Y, the W is also sent to a different W. Bizarrely, it doesn't even have to be isomorphic to the original W. Not only does it mess it around, and this is nothing like the identity, it really messes the space up. And even in terms scheme theoretically, the W and the W hat, as it were, don't have to be isomorphic. Okay, of course, if they're generic points, then they will be, but if there are fat points, a fat point can go to a generic point. So it's really, really, really strange. Similarly, this whole region here, if you hit anything in here with a Fourier transform, it goes to here. And the 2-step complexes, of course, came from the collinears, and then it turns out that these are the Fourier transforms of the one in here. So the picture is nicely symmetric. Right, that just leaves me to say a few concluding remarks. So hopefully I've convinced you that these tori provide good toy models in which to kind of explore moduli spaces of Bridgeland stable objects and to perhaps test out conjectures such as projectivity. There's a very clear link to the geometry of the torus, and that's something I think we'll see more and more when we explore moduli of Bridgeland stable objects, that there'll be a very close link to the geometry. Okay. In the case of P2, we get a link to the kind of algebraic structure via quivers, but here we also get a link to the geometry. That's the geometry that dictates it. And that will also happen for the K3, I guess. The Fourier-Mackay transforms, of course, give us for free a whole set of new moduli spaces. And in fact, just before I came in, I just back of the envelope check of a whole load of other modular spaces we can deduce from these ones. That immediately we know that they're fine projective moduli spaces of Bridgeland stable objects with various Chern characters, and quite a lot of them are projective as a consequence of these calculations. Okay, so we get these for free, and very often they'll be two-step complexes. Okay, and actually, very often, in fact, generically, there'll be three-step complexes, and that's even more interesting. So this is automatically constructing large families of moduli spaces, fine projective moduli spaces consisting of three-step complexes. So I think that's worth exploring further. And because of the context we're working in, and the reason why this toy model is such a good one is we really can identify the isomorphism type very often. Okay, I know sometimes I said, oh, I don't know what it is in this case, but we can quite often identify the isomorphism type. And that's it. Lots of time for questions.
So there's only one of these that I guess you didn't tell us whether it was projective or not. I mean, it was M1.
Yes.
5 points. Right?
Yeah. So the five. This it wasn't M1. It was M1. M1 and M2.
M1 and M2. Do we know those are projective or not?
No, I don't know. I don't see how to prove that. Now it's worth saying that there's a lot of data available to us particularly in the torus case because these modules, particularly M0, is replete with big divisors. So it seems very likely that they can be transported through the flops, especially given this is a codimension 3 flop. So I think it's only a question of just checking that the right divisor goes through to an ample divisor on this side. So I think one can actually prove projectivity very directly in that case. Okay, but we haven't quite dotted I's and crossed T's. So I'm sure it is. I don't think there's any question that these are projective. But I haven't quite dotted all I's and crossed T's.
Any more questions?
A bit, yes.
What would be the natural replacement for the Fourier-Mackay transform?
Well, the reflection function would be the obvious one.
With OX, right?
With O, yes.
With this perfect twist with O.
Yes. But there are lots of other twists, of course, one could use. That'd be the natural choice. But you could also, the motto here is you might as well try and specialize to a rather particular variety. So why not pick your variety that gives you the nice answers, right? So pick one that's got lots of divisors and choose a nice Fourier transform, like the kind of reflective case that Ugo and co invented. That one would also, I think, give quite nice answers.
In the K3 case, you have to change the category. Yeah. You mentioned that for ambiguous surface case, Fourier-Mackay transform preserve categories.
Yes.
But in the K3 surface case, you need to modify.
Yes, so that's right. So even in the torus case, if you choose a different Q, then A beta won't be preserved.
Bridgeland, no, in the K3 surface case, Bridgeland stability, the Fourier-Mackay transform of Bridgeland, the Abelian category in which appeared Bridgeland's paper, mapped to a slightly different category.
Under the Fourier-Mackay transform?
Yes.
Well, I mean, no, it's another A beta.
Because omega square is very small, and Bridgeland showed that if omega square is greater than 2, then he constructed example Abelian category stability condition.
Yes.
But if omega square is smaller than 2, it's not satisfied with the condition of the Bridgeland stability condition. So you need to modify the moduli agent. You need to modify the Abelian category.
In particular cases, you mean?
Case 3 case.
Yeah, in particular cases of K3. I mean, generically it won't, right? I mean we're basing this on Hoybre's construction, that an A beta set to an A beta dash.
I know that in that case, moduli space only parameterizes new stable vector boundaries. In that case, okay, but you are considering the spherical twist.
Yes.
In that case, it's not correct.
Well, yeah, okay. So the problem is, I mean, there are two separate problems. One is that you want to find an abelian subcategory that's actually fixed by the Fourier transform. That you won't find in the K. Well, you might occasionally find it, but you generally won't find it in the K3 case. However, you certainly will get a transform. You will certainly get an abelian subcategory, of course, with a stability condition, right? So you just have to work in that. Now, what you do is you limit yourself to the family of objects.
In that case, you have to wall cross. You have to also you also need to consider the wall crossing along the category. There are two categories. One category is Bridgeland category, and the other is the category which omega square is very small.
Yeah, but they have a very big intersection. Yeah. So actually, and in fact that happened in this little M3 case where we applied our delta. I mean, our delta doesn't preserve A naught, but I can still deduce actually the objects and also all destabilizers are preserved by our delta. So I can use the intersection of A naught and its image under our delta, which is a very complicated three-step category. So we can do the same in the K3 case. You just intersect. Okay. So it's harder to get more generic information, but what I would expect to be able to do all of, say, L squared IX for a big range of K3 surfaces using reflection functors, simply by intersecting. But it's a good point, though. Yeah, thanks.